Alright, so in this problem 3, this is again about a confidence interval and a simple t-test. And let's just assume that in a sample of n equals 9 drug addicts, you find an average BMI of x bar equals 22 with a sample standard deviation of 4.5. The average BMI of a healthy non-drug addict is 25. And those are made up numbers. So, okay, conduct the two-tailed hypothesis test at alpha equals 5%. Specify the null and the alternative. Okay, so the null would be that the population mean, mu, is actually equal to 25. So, and the alternative in a two-tailed test is no, the mean is unequal to 25. So in this case, we need to work with a t-score. Why? Well, even though we know the population average, for whatever reason, we don't know the population standard deviation, and all we have is our sample standard deviation. So we have to work with a t. And that's the next question. What is the critical t-score at which you would reject the null hypothesis? Okay, so now the t-score depends on the sample, and because our n is 9, it follows that we have 8 degrees of freedom. And because we want to do a two-tailed test, we have our critical t placed where we have on each side 2.5%. So this area is 2.5 and this is 2.5%. So the question is, what's the t-score? Well, we can ask Excel for that, and we use t.inf inverse. And the formula is 0.025, degrees of freedom 8. And then we get the critical value once at negative 2.306. And positive 2.306. So those are our critical t-scores. So the critical t-score is plus minus 2.306. And how many standard errors is a 22 away from a hypothetical mean of 25? So within the population, where we have here the BMI, here we have the T. So our distribution looks like this. We hypothesize that the true mean is 25, or we know it is 25, but we got a sample of 9 which averages out to 22. So the question is, how many t-scores is that away? Well, for this, we need to use the t-score formula, which is 22 minus 25 divided by the standard error. The standard error is the sample standard deviation of 4.5 divided by the square root of n, so that's 3. So our critical t is negative 3 over 1.5, which is negative 2. And we can see that our test statistics, or our rejection zone, is here to the right of 2.36 and to the left of negative 2.306, but our test statistic of negative 2 is inside the rejection zone. So here the answer is for 3, -2. And what do you conclude? Do you reject the null, or do we fail to reject? So we fail. But now conduct the same hypothesis test as a one-tail test. And of course I want to show in the alternative you put typically what you want to show, that those drug addicts, they are statistically significantly undernourished, so they are less than the mean of 25. But then because the HA and the H0 need to be mutually exclusive, the null is greater than or equal to 25. So how would your result differ from the two-tail test? Okay, so to figure that out, we actually have to look into it again. So we have the BMI here, and we have the distribution. And we hypothesize, or we know that the true mean is 25, but we have gotten a sample which averages out to 22. Okay, so now we need to know what is actually the critical T in a one-tail test. So if I want to do a one-tail test, I need to find the T where I have all the 5% to the left. So that means I need to go to the T inverse, and I just change the probability from 0.025 just to 5%. Okay, so now we get 1.86, and we know that to the left of negative 1.86, that is our critical T. T critical, that is negative 1.860. So that is the rejection zone. So we have only one rejection zone, which goes to the left. And nothing has changed with our test statistic. The test statistic is still 2. So nothing has changed here. The 22 away from a 25, that is still 2 standard errors below the mean. So that means that this time our test statistic is in the rejection zone. So that is our test statistic, T test of -2, which is clearly in the rejection zone. But we could have made a type 1 error, right? You know, it still could be that those 9 drug addicts are actually perfectly healthy. They are not undernourished, they are well fed, and they just happen to be on the skinnier side. So the remaining probability that we made a type 1 error is this area to the left of our test statistic. And because it is a one-tail test, I don't have to multiply anything by 2. So in this case, we will say that we need T dot dist. I want the area to the left of -2. If you have 8 degrees, when you have 8 degrees of freedom, and you want it cumulatively, because I want that area. And of course, it needs to be less than 5%, and it actually turns out to be exactly 0.04, or if you have more decimals, maybe, around 4%. So that means there is still a 4% chance that we reject the null, even though it is true. But, that's the risk that we take as a researcher. Okay, so the last question is, from your sample, construct the 90% confidence interval for the population mean. Okay, So the logic here is we have our distribution, and I assume when it comes to the confidence interval that my mean of 22, well, let's assume that this is for now the true population mean, but then you're not certain, and you build a 90% confidence interval around that one. Okay, so if you build a 90% confidence interval around that one, that means you have in the right pocket 5%, and here you have 5%. So now here we have everything in terms of BMIs. So now we need to convert that problem into T, because the formula for the 90% confidence interval is sample mean plus minus T, where we have in each pocket 0.05 with 8 degrees of freedom times the standard error, which is the sample over the square root of n. Okay, so what we need to find is the T, where we have to each side 5%. Okay, so in this case we use the formula T.inf open parentheses 0.05, how many degrees of freedom? 8. So the t-score is plus minus 1.860. So that means to the left of negative 1.860 and to the right of 1.860 I have 5%. Okay. So now we have 22 plus minus 1.860, and the standard error is the standard deviation from our sample, which was 4.5. So that was given up here, 4.5, divided by the square root of 9, which is 3. So therefore, we get the lower limit. So now the lower limit is equal to 22. Okay, so now I have to do minus 1.86, so I can actually do plus, and then pick up the negative from the T.inf formula times 1.5. Okay, so then the lower limit is 19.211. And the upper limit would be equal to the mean of 22. And now I take minus, and then the other minus from here, from the T.inf formula, it becomes positive, times 1.5, 24.789. Okay, so we can also write that confidence interval something like this. We put it into brackets, and then we just say 19.211 is less than or equal to the population mean. It's less than or equal to 24.789. And yeah, that would be the 90% confidence interval. So the 90% confidence interval would not include the population value, but maybe a 95% confidence interval. Okay, so let's stop here, and then let's continue in the next one with a simple t-test, but let's do that in a separate video.